Hello everyone, so today we're going to continue on 8.4. Hopefully today's video is the last video because I only have one last thing I want to show you, and that's called the curl of a vector field. So imagine the following. So let me put up a vector field so we can take a look at it. So maybe we'll just do this same one that we used last time. This one right here. So now this seems to be pretty simple when you kind of think about the flow line. You can see that the flow line kind of starts from the origin and curve out and backward like this. Okay. Now here's a very interesting question. Imagine that you have an object like this floating on this vector field. Now if this object actually takes up some room, that would imply that the vector on one end of this object would probably be different than the other end of this object. Now, granted that they probably all still going in kind of the same direction, but the problem is that it might not be exactly the same speed. And therefore, assuming that, let's say on this end, we have a stronger vector, maybe not blue because it will blend in, stronger vector going this way than this side. If that's the case, the object will still be moving in the direction that both of these arrows are pointing, but because one side moves faster than the other one, what would happen is the object actually would tend to rotate around due to the speed differential. Now, it's actually not an unusual phenomenon that you haven't seen in real life. As a matter of fact, this basic concept gives rise to a tornado, which a tornado would be moving in a certain direction, but as it's moving, it would constantly be having this circular twister motion within itself. And the reason why it has this motion is precisely because of a differential of speed between kind of the two sides of the tornado. So this concept of an object rotating around itself as it moves through the vector field is what we call curl. So let's try to write down what does it mean, or what is the curl of a of a vector field. The curl of a vector field basically described the tendency of a neighborhood, which is basically what this small disk represents, a neighborhood around a point, to rotate due to the flow of the vector field. So which is the reason why it's called the curl, because it's actually talk about how the vector field rotates around itself. Visually, what curl does is the following. Visually, if the neighborhood around a point is, let's say, spinning due to the movement of, due to the basically the speed differential, but basically due to the flow of the vector field. What does the curl do is the following. So if a neighborhood in D is rotating or spinning around based on the movement caused by the flow, then the curl will allow us to determine the following. Allow us to determine the direction of the spin, of the rotation, and the speed of the rotation. Now, because the curl actually have to define two things, we need to find this curl that will allow us to convey two different pieces of information: the direction of the rotation and the speed of the rotation. And therefore, that is the reason why curl of a vector field is a vector. So different than divergence, which is a scalar, the curl of a vector field is a vector. So how does this curl work? The direction of this vector of the curl basically identifies the axis of revolution. So it defines the axis of revolution, and the direction of the rotation will actually be following the right-hand rule, where when your thumb points in the direction of the axis of revolution, the way your fingers curl will define the rotation. So the direction of this vector basically means the direction of the curl indicate the axis of revolution with the direction of rotation follows the right-hand rule. And the magnitude, the length of the curl indicate the speed of the rotation. And here you can basically understand that the longer the curl, meaning the longer the length of the curl, would indicate a faster spin. And because the magnitude is always a positive value, it doesn't indicate the direction of the rotation, because that is dictated by both the direction of the curl, which indicate the axis of revolution or axis of rotation, and also the right-hand rule, which indicate which way the curl would rotate. Unfortunately, I cannot really show you a picture to illustrate what the curl is, because it will require an animation, and I really don't have that capability of doing that. Lucky for you guys is I did find a video that talk about curl and divergence from the math channel that I mentioned in class, the 3 Blue 1 Brown channel. So I'm going to post the link of the videos, and I strongly recommend that you watch it. It's a very good video with a lot of cool visual that can show you some of the idea. The only difference is that the curl that they in that video is actually what we call a two-dimensional curl, which is not the same as the curl that we talk about, but related. And you can still kind of have an idea as to what does it mean by having a curl. So still a good video to watch, and it definitely would enhance your understanding. So please make sure you find time to do that. So now come the big question is, how do we actually calculate the curl? Well, the curl, we're only defining the curl in R3 because of the way we calculate it. Does that mean that in high dimension there's no curl? Well, maybe there is, but that's not part of this course, so therefore we're not going to talk about it. So in R3, actually, let me probably just give you a definition and try to see how I wrote it for the divergence. Okay, so I guess I just write a definition, so I'm going to go and do that. So we're going to define what is the curl, but specifically in R3. So here's the definition. So let's say given, a vector field F. And let's say F met from R3 to R3. So as I say, we only go define the curl for something that's in R3. So such that vector F is equal to F1, F2, F3. I'm going to drop the vector X as the input because we kind of know that's the case. We're going to go and let this upside down triangle, which is the gradient symbol, be the gradient operator. So it's defined the same way as in the last definition in R3. So that means gradient is equal to d over dx, d over dy, d over dz. Remember, it's strictly in R3 right now. Then I can define the curl of f to be given by the following formula. The curl of vector f is given by the formula. And the notation for curl is C-U-R-L. I'm actually very surprised that the notation for curl is actually 4-letter. Because, I mean, we know mathematicians don't like to write, and they even cut off one letter is important to them. I mean, just think about sine, ratio. I mean, the word sine is S-I-N-E, but then we used S-I-N as the notation. Okay? So curl of vector f is actually equal to the gradient operator cross product with f. So therefore, you have to kind of remember how to form cross product back in chapter 1. So if you apply the cross product to the gradient vector, to the gradient operator and the function vector f, which is f1, f2, f3, you find out that they actually form this vector, df3 over dy minus df2 over dz, df1 over dz minus df3 over dx, and df2 over dx minus df1 over dy. So that's the formula for the curl. And because it's using a cross product, it actually forms some kind of perpendicular vector. And if you think about it, it makes sense, because whenever something rotates in a circular motion, it requires the force and the speed and the velocity to be in some kind of perpendicular direction, which is kind of the essence of why the gradient cross product with vector f would kind of give you a value or a vector that can define which way the object rotates. Now, give you a very simple example to illustrate. Let's say we have vector f of x, y, z to be equal to, I don't know, y, z squared, x to the third. Then we're going to ask you to find the curl of vector f at the point 3, 2, 1. Okay, so let's go and give it a try. To find the curl of vector f, I simply use the formula right there. So before I use the formula, maybe I'm going to write out the 3 functions that we have. f1 is y, f2 is z squared, and f3 is x to the third. And I purposely kind of leave the formula right on the top of the screen, so I'm going to just directly use it, because f1, f2, and f3 seem to be very easy function for me to differentiate. So there's no reason for me to actually write them out again. I can just differentiate them in my head and just write out the answers. So let's see what this is. So for the first coordinate with df3 over dy, df3 is x, f3 is x to the third, over dy is just 0. Minus df2 over dz, so therefore it's minus 2z. The second coordinate is df1 over dz, which is 0, minus df3 over dx, that would be 3x squared. And then the last one is df2 over dx, and f2 is z squared, so when differential with respect to x is 0. df1 over dy, which is 1, so it becomes 0 minus 1. So it seemed to me that the curl of f would equal to negative 2z, negative 3x squared, 1. So now I'm going to evaluate the curl at the point 3, 2, 1. So the curl of vector f evaluated at the point 3, 2, 1, which is basically equal to negative 2, negative 3 times 3 squared is negative 27, 1. So now we have an answer. So what does that mean? What does that answer mean? So that answer actually identifies kind of like an axis of revolution. Or axis of rotation, which is this vector negative 2, negative 27, 1. And it indicates that the way the rotation works, which basically kind of rotating around like this. So whichever this axis is pointing at, that would be the rotation around it's going to be. And depending on how long this vector is, the longer this curl is, the faster the spinning around it would be. And once again, it's probably hard for you to visualize what's going on, but hopefully after you watch the video from the YouTube, you'll be able to kind of have a better idea when you see some of the animation being presented to you in the video. So last thing I actually want to talk to you about would be following, and that would actually be what the video actually talk about when you have a two-dimensional vector field. Can you somehow calculate curl? Because it seems to me that the way we define curl is only in R3. So for a function f that met from R2 to R2, we can still calculate the curl if we assume the vector field is actually just on the xy plane, which means the third coordinate is actually 0. And if we do that, then notice what will happen is the following. So instead of looking at the function f that met from R2 to R2 being a function f equal to f1, f2, we go transform this function into kind of function that met from R3 to R3, and the vector field is just equal to f1, f2, 0. So that way, every vector field is actually parallel to each other, which is exactly the same as the vector field that actually lie on the xy plane. And if that is the case, notice the following. If that's the case, notice that the gradient cross vector f, which is basically what the curl of f is, would be the following. Because of the function f3 is 0, and we also can kind of assume that z becomes 0, we can then assume any partial derivative with respect require you to deal with f3 would go to 0, and because of the way none of the function f1, f2 is actually dependent on z, because remember they are function that went from R2 to R2, therefore they don't have a z in them. The partial derivative to z would also come out to be 0, and therefore turning our curl becomes 0 minus 0, 0 minus 0, and then df2 over dx minus df1 over dy. Remember, because f3 is 0, any derivative involved f3 will be 0. And because our function f1 and f2 is not dependent on z, because it originally comes from a function map from R2 to R2, therefore only have two independent variables, any partial derivative involves z would also have to be 0. And therefore forcing our curl to actually become this thing. Notice that because these two numbers are 0, this curl is pointing in the z direction. And because of the fact that these two are 0, the value, the length of this vector is actually just simply equal to this last coordinate, whatever this value is. And because in this scenario, even though we do have a vector as a curl, because of the fact that we're doing a vector field that map from R2 to R2, the first two coordinates of this curl would guarantee to be 0, therefore imply that any kind of curl for a two-dimensional vector field will only be pointing in the z direction. And because of the two zeros, the last number represent basically the last coordinate would also basically represent the magnitude of the vector. Because of these two things, this expression right here has a special name. And we'll actually see this expression used a lot in chapter 9. So make sure you understand and remember this formula. df2 over dx minus df1 over dy. This expression is what we refer to as a scalar curl. Basically, what does that mean? Meaning it's a curl for a vector field in R2. It's called scalar curl. And that actually is what the video from the YouTube channel 3 Blue 1 Brown is showing. Is that it's showing a two-dimensional curl, which is basically a scalar curl. How to calculate a scalar curl is actually the exact same way as you normally would do, but you actually present it as a scalar instead of as a vector with 2 0 in front. So let's say we have, let vector f of xy equal to, let's say, negative x plus y, negative x minus y. I'm going to go ahead and ask you to find the scalar curl of vector f. So how do you find the scalar curl? Well, the scalar curl of f is simply just equal to df2 over dx minus df1 over dy. So therefore, now once again, both of these functions are simple enough that I can just simply do it in my head. So in this case, df2 over dx is negative 1. And df1 over dy is 1. So become negative 1 minus 1, which is negative 2. So therefore, in this case, it indicates that because the value is negative, it indicates that the direction of the vector actually is point downward. Oh, actually, you know what? I do want to amend that, meaning it's the absolute value of this expression. So the scalar curl is negative 2. The magnitude is technically 2. So that's kind of indicate how fast the rotation is. Because negative 2, it would indicate that the vector actually point from the xy plane pointing downward. Indicate that when you look at it, the rotation is actually clockwise. But in the case that the curl is positive, then the axis of revolution actually point upward from the xy plane, and then the rotation would actually be counterclockwise, while its point downward would be clockwise. So once again, it's hard for you to visualize that, but watch the video that I'm going to post and you will be able to see it better. Unfortunately, that's the end of 8.4, and so that would be it, and that's everything you need to know before your next test. So make sure you watch all the videos, and make sure you start studying for your tests. And that will be it for this video. All right, I'll talk to you guys soon. Bye bye.